Okay, good morning, everyone. Let me turn off my mobile phone. Right, so seems to me most of you guys actually can do an online course now. We had last week I had 7, or today one at the moment only 2 here. They are the postgrad. Okay, let's just continue on the acquisition we started last week. So one of 2 important sources for land seismic is this stuff here, big truck vibration for the vibrate for vibration. So the fundamental mathematical theory for this type of method is cross correlation. So we send up a sweep, which is the harmonic signal, but with the variable frequencies, and you record so-called record data, and then you correlate with the source signature. So let's move on. So this type of source is relatively, compared to the dynamic source, is relatively weak in terms of signal, but based on the superposition, the linearity we discussed last week, you can time invariant and linear, so you can basically acquire data many times, and they just simply stack them. You can have an enhanced signal. So that's this positive thing. The negative thing is because the source in the surface, so it's very easy to generate noise, so-called noise here. Right. How to suppress noise in the field? One of the technologies called use not a single receiver, but a group receiver together, okay, as a single channel. So you saw your seismic data as a single channel, but in field, this single channel or single trace actually were acquired by a number of receivers, right? So not a single receiver, a number of receivers. The aim is to reduce the surface waves. Let's show you the mechanism here. Okay, you have a source, receiver, right? So if you have a source receiver, you see the wave propagating around horizontal direction. That's the surface wave. But if we have multiple sources, not a single one, they actually, the horizontal components somehow cancel each other, and then you enhance vertical energy, right? So this just what I said, a group of single trace, okay, a group of, well, here is talking about a group of sources actually, right? But also similar mechanism as a group of receivers, same principle. So for example, here is a single receiver, but received from 4 sources. So the horizontal components there, because they're out of phase and they cancel each other. Time, out of phase means the time delayed, right? We're talking about phase last week. Phase means time delay. So this source generated one harmonic wave, and the second one, but they have a time delay. So different phases, okay? If you sum them together, they cancel horizontal component. that was source. So now we're talking about the receivers. Traditionally, because the seismic acquisition starts from land activity at a very early stage, so we call the receivers called geophone, right? But in the later stage in the marine environment, the receiver we do not call geophone, we call the hydrophone because they put in the water, right? For the geophone basically, single geophone has two parts, important two parts. One's coil and magnet, right? So basically, when you surface have a vibration, right? So these two parts, they have a relative movement, okay? So relative movement actually transfer to the voltage of electricity, right? And what you record is basically the voltage of electricity, okay? And some practical part, including damping at the very beginning, and then occasionally use a flat base. So this is what we're talking about now. Okay, this looks like the geophone. Actually, this one we call it geophone, right? And that one is it's not exactly geophone. This actually in the shallow water. It's still on land acquisition, but there's some mud area. Okay. So this is called a mesh phone. That's one called a geophone. Geophone looks like this. So the inside of geophone is this one. Have two parts. The coil, which is this one, and then the inside is a magnet, right? So this is the mechanism how a geophone works. So when the surface is shaking, you have a particle movement, and so this spring coil actually have a relative movement against the magnet. That's give the different voltage. So actually, you record as the voltage. Right. Practically, we do need a damping in the front. This is why if anybody actually deal with real data, you know that from most time the field data are lack of lower frequency. Horizontal axis is frequency, but this is in the logarithm scale, right? Horizontal frequency. So most likely from 0 to 8 hertz, they're missing from the field. Why is that? Because they have a damping in the field, okay? So the damping, you try to, the most ideally, you have a flat top response, right? And to achieve that, you need a bigger dump in the front, okay? So here they have three samples. One's three examples. One's 34%, 50%, and 70%. When you have 70%, you have an ideal flat response. Okay. So basically, the vertical axis is a voltage. As I said, what you record from the geophone is a voltage, right? So the voltage units is per second, per inch voltage. Okay. So it's a that was the mechanism of geophone, but in the acquisition in the field, one importance is called coupling. Okay, when I started as a geophysicist, I worked in the field, so my job is to, 10 kilometers sort of distance, you just walk around and just, let's say, plant your geophone on the soil, into the soil, okay? That's quite actually tedious job, but really important because this is really important for the fidelity of your data. You cannot simply, use a foot to punch that. No, that's what damage your geophone, okay? Because this geophone have a soil inside, a coil inside, right? So if you damage that, the recording instrument, they know immediately you damage some phone. That's really a big trouble. Okay, you need to carefully plant into the soil. So pole coupling will introduce amplitude phase distortion. So they also can know that. Good coupling, requires careful planting. Okay, here's a planting here. So that's in the field, and I don't know any of you will have a chance to do that. Actually, it's quite interesting. When I was in the university, I don't know what's the equation, whatever equation will be. So I couldn't imagine this mathematical wave can link to the actually seismic waves. But when you go to the field, you actually know exactly where this wave came from. You understand the concept better. Anyway, as I said, we need a coupling. In the previous example, I showed you the coupling of a number of sources. But here, I show you coupling of receivers. Okay, so in the field, usually they're manufactured as a string. So the number of receivers that they're manufactured as together, and then they transmit the summed the data into the channel, so-called single trace. Okay, so number of several geophones together generate a single recording, so-called trace. I repeat, so single seismic trace in the field is not acquired by a single receiver. Okay, it's acquired by a group of geophones, let's say. But in the theoretical study, you just think, okay, I have one receiver, but one receiver really means one receiver point, right? But in fact, physically, maybe 5 or 6 geophones. The same principle as the coupling of same principle as a group of sources. This is also for reduced coherent noise. Let's show you again. Similar diagram. Have a single source, single receiver for each point, right? So you have a horizontal, so-called ground roll or near surface surface web, and then if you have multiple receivers, you can see the vertical component enhanced, but the horizontal components somehow they cancel each other. So this is the principle. Okay, so this both actually were in the field.
The attendance for the seat.
For the signature.
Yeah, it's for the seat login.
For the students.
Yeah, seat register for the students.
Okay.
Once we're done with that, we'll just note the seat. They will note the seat where they're seated today. And you can just drop it at the immigrant office.
Okay. Sure. Right. So, including the student online or no?
No,
just the physical here.
You can take the online attendance copy at the back.
Sure. Okay. Yeah. Thank you. Right. So that's a typical acquisition. I said in the field you need a number of sources, but because the vibrate is quite heavy. Actually, it's not the exact number of sources. It's a single track, but they move, shift, in a constant distance. Because the two assumptions we made last week, linear and time invariant, so that just can treat as 3 or 4 vibrators, right? And the receivers, of course, they already put in the field. So each of the here maybe have not only single receiver, but have 4 or 5 receivers. Okay, so this is the typical acquisition. Now, we're talking about a marine acquisition now. In the marine environment, because of, as we said, in the water layer, we cannot, the modulus of water shear modulus is 0, right? So we cannot record the particle velocity. Only we can record is pressure, okay? So basically, this is what we're recording. So when you have a pressure, compressed water, or expanding, right? So you just recording the pressure. That's the marine environment. And in the marine environment, your upgoing wave and the downgoing wave, they are just summed together, right? Okay. If this one put on the surface, near the surface, the water surface, the reflectivity is -1, almost -1, because you do, if 100% reflect back, that means you cannot hear the sound from the top of the water, right? But if you can hear anything, that means you have energy propagating through the water surface to the air, right? So, but almost, okay? So so that means in the surface, you have a upgoing, downgoing, some of each other, but here have a -1. So basically, they are 0, right? The summation is 0. So what we need is we cannot put either source or receiver exactly on the surface, right? We must put the source and the receiver below the water surface, okay? So what we are going to discuss in the next few minutes, we just see how the depths of source or depths of receiver from the surface affects your recording seismic data, okay? That's what we want to see. So, first of all, because in the water environment, you only can record is a P wave, which is a compressional wave. P stands for primary, okay? So it's for compressional wave, okay? And in the water, the velocity roughly 1,500 meters per second, but it's not exactly, okay? Because the velocity depends on somehow related to the temperature, related to the water actually also have density changes because of salt, something, right? But for the accuracy requirement for seismic data, I think this 1,500 is universally acceptable, right? As I said, we do need to put both source and the receivers below the water. So that means we introduce something that's called a ghosting. Okay, now I'm going to explain what is ghosting. Right, this water surface. Here, a source of water in the water, right? You have a propagating wave downgoing, but also have wave upgoing and downgoing, right? So basically, this wave going to up and down. You have a downgoing wave and downgoing pressure, upgoing at this point, right? Okay, because just for the illustration here, I just have a angle here, but you just think about this vertically going up and going down, right? So this wave going down, this wave going up, come down, and these two waves have one distinguished feature, which is the phase delay. Okay, so phase delay means time delay. You can see one's here, you're going down, another one going up and come back, maybe take a 6 meter up, 6 meter down, so take a 12 meter, time delay. So you can one's the original one going down wave, another one's up going and down back, right? You can see now, instead of an ideal simple wavelet, but now we have a slightly complicated wavelet, right? So this one follows this, and Actually, it's -1, you see that? 100% COVID. So it's just ghost. Just like one person walk in the front, another ghost follows. Yeah, that's called a ghost. Right. So that was the source part. And the receive part, you have a receive here, right? Your wave propagating reflection from subsurface going towards the surface of water. Here you pass on that, you get an outgoing pressure, and then going to the top, and the reflection from interface between the air and the water come back. So you have a downgoing wave, right? So basically what you record here is like just two combination, right? And between these two, they have a time delay. And the phase peak and the trough, they're exactly copied, but in the imaginary manner. So this is the ghost. So, okay, because we cannot record pressure on the surface, we must put the source and the receiver below the water surface, right? So that, because this acquisition geometry, you both source side and the receiver side will generate so-called ghosts, right? Source ghost and the receiver ghost, right? Now, last week we reviewed something called a Z transform, and based on Z transform, we easily lead to the DFT, discrete Fourier transform, if we recall that. Okay, I put it there really actually in this whole course, almost every step you can use this very simple, straightforward Z transform to do the mathematical calculation, even you didn't learn much about the sophisticated DFT. Okay, so let's just show you example here how to determine in the field, how to determine the depth of a source and the depth of receiver. Okay, so based on this surface ghost. Right. If we record that in the Z transform, the Z transform basically transfer a sequence, a series of time samples into a polynomial, into a sum of a number of terms, right? Okay. So for each term, you have a coefficient. The coefficient basically, each coefficient is the amplitude of that position. And you have Z term. The power of Z is the index, time index from 0. From index 0, but basically time index, okay? So now for the ghost, we have two samples. One from here at time 0, let's say. Okay, you record here, we just call time 0. Amplitude, we just assumes 1, normalize is 1. And then this is where we're going to up, down. Up, down, the reflector here is -1, remember? Okay, which is for the generosity, we just call R. So the first term, first sample is 1, another sample is R. The index of R, which is time index, right? How to work out the time? Basically, the travel from here go up, come down, the distance divided by velocity. Yeah? That's the travel time, and divided by the time sample interval. You can see here, the distance is a 2D, D steps, right? Going up, 1D, come down, 2D, right? 2D divided by the velocity. Velocity we know is water velocity, right? We already said, just in the previous slide, we said it's 1500 meters per second. That's the continuous time, right, with T. But in the Z transform, we use the index. So assume the time sample interval is delta T. So basically T divided by delta T, that's the index. Okay? So in this time series, you have 1 and R at index of 2D divided by V delta T. That's a perfect example for the Z transform, okay? Now, that's the index N here, 2D divided by V delta T. So now if we recall that Z is unit time delay operator, okay? So it's E minus I omega delta T. Omega is 2 pi F, F is the frequency, right? So you end up this one becomes this formula because R was -1, here is the N, okay? Now we do the calculation now. If we substitute Z by the operator of EI omega delta T becomes here minus EI 4 pi F D divided by V, right? Okay. Now, this is a very simple calculation of complex value. Here's 4, so I just take out half of this to have E minus I 2 pi F D in the front. Inside, we have one's positive, one's negative. Why I do that? Because I can cancel cosine part, right? So this one becomes cosine this phase minus plus I sine this phase, right? Here's cosine this bit, I minus sine this bit, right? So that cosine and cosine canceled, you end up inside end up as minus 2 sine and this phase, yeah? Okay, here is 2 sine of this phase here, okay? Where's minus I? Where's I gone? I is here. This one's I. E minus I pi, half pi. That's I, okay? So now you can see why I present it in this way, because this is a pure complex value, because the modular of E here is 1. That's pure phase, right? And the front here is pure amplitude. So I presented this as a modular and a phase. You learn the complex values, right? You have modular and a phase, okay? So now you can see that if we, at the moment, if we ignore the phase, which is talking about amplitude look like this, okay? But here, this one is not purely amplitude, not a purely positive amplitude, which means modular. Modular means squared real part plus squared imaginary part and the square root. That must be non-negative value, right? But the sine here, you can have negative value. So basically amplitude, you have absolute value of sine, yeah? So this, the amplitude spectrum. Instead of a sine function, it looks like this, come down, come back. But because they use absolute value here, you end up sine look like this, yeah? So from here to here, basically, it's a pi. If phase is pi, right? When phase 0, amplitude 0. When phase is pi, amplitude also 0. And the 2 pi 0. So basically, period here, that's 1 pi, 2 pi, right? You end up, you find out F1 here. Why I put N here, N called notch. So in your seismic amplitude spectrum, horizontal axis frequency, vertical axis amplitude. And you can see the notch here. So this, when you do the analysis of real data, you can see the notches here, right? So this notch is based on the velocity and the depth. Velocity fixed, depth depends on your real case. Now you can see the notch depends on the depth, right? Okay, so the ghost will affect your data spectrum in terms of where's the notch, right? Now, if D is larger, means Fn smaller, right? Means Fn smaller. Fn smaller means this from here to here, the variable signal become narrower. Okay, now how to measure this? Usually we measure from top to the highest amplitude, half the highest amplitude, we measure the width of this. That called bandwidth, frequency bandwidth. Okay? The bandwidth we do not measure like up to the almost zero amplitude because it's hardly find out one, right? So that's standard way. You have a highest amplitude as a 1 and a half amplitude is here. You measure the width from here to here. That's called a bandwidth. Okay. Now, because the notch depends on the depth, that means the bandwidth of your data depends on the depth, right? So now you can see the acquisition source. In the acquisition, the source depth relate to your final bandwidth of your data. See the relationship here, right? So you can see very simple math here. Do not just think about the math, but think about physics. Okay? So basically, if for air gun, for the exact surface, we cannot generate, cannot record the pressure, but we need to put it down to the water. Okay? But how deep? Right? This is the trade-off here, right? The deeper may be quiet, but the bandwidth is narrower. Shallower may be noisy, okay, but the bandwidth is wider. So this is the trade-off here, okay? Right. That's for the. Okay, I already said this. If we have a highest amplitude, in this case is 2, right? You can see here, 2 multiplied by absolute size. Okay, so maximum magnitude here is 2. Now, so half of the maximum amplitude, which is 1 here, you measure this one's bandwidth. Right. This I'll give you 2 examples here. One depth equal to 5 meters. And the first notch is 150 hertz. You can see that 5 meters multiplied by 2 is 10. V was 1500, right? 1500 divided by 10 is 150 hertz. You see that? And half measure at a half amplitude is actually 25 to 125 hertz. Okay. Right. If it's the depth 5 meters, your bandwidth is 25, 125. Okay. Another one, if much deeper, 3 times deeper, because these 3 times, so your Fn is 3 times smaller. You can see the bandwidth becomes between the 8 and the 41 hertz. You see that? Okay. So that's we're talking about the ghost in either source or receiver in the marine. They are same, right? They are same. So now, a typical marine current stage, typical marine acquisition geometry is this. Source 6 meters. You can work out the ghost notch is 125 hertz, right? Why we do that? Because 125 hertz, we're talking later about next frequency, because this will be related to the sampling rate. Sampling rate of 1/2 delta t is called next frequency. We'll talk about it in a few minutes. So this means in the field we can use like 4 millisecond sample interval. Okay, that's also everything related. So effective bandwidth is 20 hertz to 104 hertz, right? So you can see in the field we do lack of lower frequency. low frequency component. Okay, nowadays when typically for PhD study, when you do the waveform inversion, you do need low frequency, but in the field we do not have low frequency. Okay, so that's the problem. Receiver usually between 8 to 10 meters. Okay, so the ghost notch is about 75 to 93 hertz. 94, okay. Deeper cable, quite as I said, but deep cable, the ghost notch smaller, narrower. Okay, so that means source 6 meter, receiver, for example, receiver 10 meter. What's the effective bandwidth? Basically, maximum 75 hertz. Okay. Net between these two, which was narrower. So that means most likely only record from 27. So if you want a shallower, right? So 80 meter probably is the best one. 80 meters have a 93, 94 hertz. Right. That was, we're talking about the ghost. Now we can see how people can effectively reduce the ghost by designing. Okay, we can see this is the ghost. This is one primary wavelet. Have this one, and well, this is basically the single impulse, and then they have the water bubble gradually bubble out, right? So you have a lower frequency and gradually decayed, and that the ghost just identical to that, but it just have a -1 and a time delay. You can see effectively you record the wave look like this. Okay, so in the data processing, one of the first stage of processing called de-signature. What a de-signature means, you try to somehow remove this, only keep that. Okay, so we are in the latest stage. One of very mature technology is called predictive deconvolution. You know exactly from here to here the prediction distance. You know this one identical to this called, so it's predictable. That's called a predictive deconvolution. Based on this, and you predict this one and then cancel that, right? That's called predictive deconvolution. That's the important one. Very fundamental technology, fundamental tool in the seismic signal processing. Right, now, what you recorded, actually? Of course, you have Earth, subsurface structure, but now you have a source, not only source, but you have a ghost as well. You have a receiver, but not only receiver, you have a receiver ghost, receiver and receiver ghost, right? And from the receiver to your recording instrument, you have a called instrument effects, right? Response plus noise. So this altogether is the form, the waveform you recorded, right? So now we just simply shift this subsurface structure. We put all the facts together, which call this a wavelet. So now I try to explain to you, when you're talking about seismogram, talking about wavelet is not exactly the source signature. You can see source signature only if we have an equivalent weights, right? But it's not. Instrument may be less, but ghost, receiver, and the receiver ghost, they all play a role, right? So the final seismic signature, seismic wavelet is not only seismic source signature, but it's the combination of this, right? This does not include the subsurface effects we were talking about later, okay? So we have much more complicated. But practically, when you do the wavelet acquisition, wavelet estimation, you estimate all the combined effects. Okay, so this is the difference here. Now, that was the acquisition geometry, but now let's talk about instruments. First of all, for the source in the marine, in the land, we have two major type of sources. One is dynamic, one is vibrate, right? In the marine, because in the water, we cannot have those two. Most likely we use so-called air guns, okay? Typical air gun have a 2,000 to 3,000 PSI, very powerful, and have generate a large pressure pulse. We saw the picture in the previous slides, okay? And have bubble, which is a lower frequency behind that, right? And sometime they tried to use different size of air gun. The size means a different pressure, right? Combine them to try to reduce or somehow cancel the bubble, right? This is the acquisition. This is a typical air gun construction here. So that's for this chamber here for the pressure. So you have air came down from side, go to here, right? And then you press that, and then you relieve this up, and all the air go to this two sides, generate a bigger bubble. So the air gun principle is generate a bubble. Okay. So this is the illustration. Okay. Now this is the way how the air gun operated. This is the chamber, the air from here going down there, right? So you have a high pressure, and then you pull up this the door here, and then your air went to the water. Okay, generate a bigger bubble. So it's a perfect point source. Okay, in the middle of water. So that's the air gun, and for receiver in the marine environment, we call the hydrophone. Basically, in the industry, we just simply call it hydrophone. The hydrophone, same as the land seismic data acquisition, is not for single point, for single trace. It's not only single sensor, single receiver. It's also a group receiver combination, right? So that's important. And just like I mentioned it for land seismic, this group of receivers, they actually already manufactured together in the field, okay? Maybe they're 3 meters apart, they put together. The inside of a hydrophone looks quite similar to the geophone, but the structure is different. This is a piezoelectric electrical material to generate the voltage. Basically, they also record the voltage, okay? But use piezoelectric material rather the magnetic coils. So it's slightly different. And usually the hydrophones spread over 12.5 meters. So one group and another group in between, because they're already fixed in the cable in the marine, right? Fixed in the cable, the distance is fixed by manufacturing, right? I just emphasize for single point at just like 12.5 meters. This is not single sensor, it's a group sensors. Okay, so this 12.5 means the distance between different group sensors, not single sensor. Okay. So now, why they need a group of the receivers? We just similar to lens acquisition. For the group of them, you can enhance the vertical component, and because of time delay, so-called out of phase delay, right? You can cancel horizontal wave components, right? You first imagine your wave decompose into vertical and the horizontal one, so horizontal cancels you, and then you sum this together, you enhance the vertical component. That's the way. Reinforce each other. Now this typical cable, it's actually quite conventional. It's the older one. Modern days much better. The older one is, you can see here, this one hydrophone, but they're put in the inside the cable. What's inside here? They actually also fluid inside, just a mimic in the marine. Outside the cable, water, will be the water, right? Inside is also liquid. So just like liquid in the liquid. Well, that's quite conventional. Okay, but nowadays this becomes a solid. Why it would solid? That will be the good reason is it will be much quiet, because inside of the cable, water will have a shaking effects, right? So have a bit of noise. So this one is cable, and everything inside you cannot see. Okay, that's more robust because than the fluid field streamer. So this is one line we call streamer. So every 12.5 meters, you have a group of receivers. So maybe 6 kilometers long or 12 kilometers long. It's a very long cable. Apart from this two, source, receiver, and another important thing is, because we need to put the receiver below the water, cannot only put on the surface, right? Because we cannot record pressure. We need something to control the depth. Typically, for the streamer very long, you do need effective control the depth on this constant level. So there's this thing called the birds to control the streamer depth. And have wings, just like a small boat in the water, you have wings, okay? Automatically adjusted based on your, if we send out signal want the depth, they automatically, up, down, adjust the depth. Quite good. And they also have a navigation information on that. You know exactly where the receiver is. Right, this is a photo from a streamer. This is a streamer, and this one is a wing. But that actually controls depth. Okay, here a receiver sensor just to send the information there and then receive the information from there. Okay. The acoustic transfer. This battery here. This is a sensor, and the cables here inside. Actually this is a traditional one. It's a fluid feeding streamer. So let me show you one acquisition movie here, marine acquisition. Can you guys online check the data here, please? Those are the streamers. It shows them maybe 6 kilometers long. Expectation actually is very high